Computer science is obviously a fundamental part of all of our lives, but I think it's important to step back to think about what we're actually doing as computer scientists. What kind of problems are we trying to solve? One of the most important things that we deal with are designing software. We want to create some pieces of software to solve important problems that we care about. But if I gave you a piece of code, you might not be able to figure out whether it actually does the thing that I proclaim that it does. And one of the most important areas in our field is software testing. So what I want to talk about in this video is some of my own research which has to do with software testing and theoretical computer science, and what we can do in theoretical computer science to solve an important problem like software testing, although it doesn't have to be that specifically. Let's imagine that we have some big piece of software, like really big piece of software. It's got a lot of components. So let's say we have components C1, C2, C3, C4, and let's say up to K components. And let's say that each one of these components has a certain number of inputs that we may want to test. So let's say that this one has 5 inputs, so these are the number of inputs for each of the components. So maybe this one has 3, this one only has 2, let's say this one has 7, and then maybe this one has 4 or something. What we want to do is we want to make sure that this piece of software does the correct thing. So what we could do is, let's say that the values for C1 are 0, 1, 2, 3, and 4. Those are the inputs associated with C1. C2, let's call them, let's say A, B, and C. C3, maybe those are Y and Z. And of course we can carry on the same thing with the other components. And what we can do to assert that this software really does the correct thing is let's just try all possibilities. Let's create a test right here. So test 1, let's have C1 be set to 0, C2 being set to A, C3 being set to Y, and then we just carry on for all of the other components that way. And then I'm going to have another test, which is going to be C1 also 0, C2 is A, and then maybe C3 is the other thing this time. And then we can carry on through all of the combinations of the components. So there are 5 possibilities for this guy, 3 for this one, 2 for this one, 7 for this one, and 4 for the last one, and etc. for all the other components that there might be. And this is not a problem that I'm just making up. These are real software problems where we have a big software system and we have a lot of different components that all need to interact together in some way. So as a practical example, it might be things that you download on your phone, or like the App Store, or mail, or the web browser, or games, like many different components. Or even you can think about components within the operating system, such as like the task scheduler and the networking stuff and the graphic stuff and all of the different things that could happen at the same time. So if we think about what is the number of tests that we would need here, it's going to be, if we just exhaustively test every single combination of here, we will have that C1 has 5 possibilities, and independently C2 has 3 possibilities, and C3 has 2 possibilities, C4 has 7 possibilities, and then eventually the last thing has 4 because that's the number that it has. And so this is going to be a gigantic number because the number of components could be huge. And so the number of possible inputs can also be huge, and then therefore the total number of possible tests that we can run is the product of all of these numbers, and that's going to be even worse. So as a practical example, let's look at the sort function in Unix. So the sort function in Unix has 18 binary flags in it. So there are a bunch of things that we could pass into the sort function, such as we want to sort things in ascending order or descending order. Maybe we want to ignore capitalization. A lot of different options that we can feed into this piece of software. And since they're all binary, they have 2 possibilities. Either the flag is false or the flag is set to true. And so the number of combinations, the number of tests that we would have to run is actually, I was going to write approximately, but it is exactly 2 to the 18, which is approximately 262,000 tests. And for a sorting function that doesn't run too long, this is not actually that bad. But if we change this to where the number of possible inputs is 3, but we still had 18 components, then this is going to get gigantic really quick. So what we would want to have is some way of adequately testing this software system without having to test this gigantic number of tests, not having to do things exhaustively. And in general, you would have to do that because there could just be some really arbitrary error that relies on a very specific set of values for each of the components in order for the fault to arise in the system. So we're going to make one tiny assumption here, which is that if we have a large number of components, let's say 1,000, just as an example. If we have 1,000 components here, then it's very unlikely that 999 components are working just fine, and then adding on that 1,000th component now causes the software to not work. It's very unlikely that's the case. What is much more likely is a small number of components, let's say like 2, that do work, but then adding a third one will cause it to not work. And so if we make that assumption, we can actually dramatically reduce the number of tests that are needed. So I'm going to introduce an object that I actually study called a covering array. So I'm going to introduce the notion of a covering array right here. So we have 5 components, just like we were talking about before. Each of the components has 2 different values, 0 and 1. You can clearly see that in all of the columns here. And it's pretty obvious that we have 6 tests. So here's test 1, test 2, test 3, test 4, test 5, and test 6 right here. What I'm going to guarantee is that these 6 tests are going to adequately test the software system for some notion of adequate. So here's what I mean by adequate. So take any pair of components right here. So let's say I pick C2 and I pick C5, just as an example, but you can pick any pair of components that you like. Then what I'm going to guarantee is that all of the ways that those 2 components can be tested appear at least once in some test. So what do I mean by that? Well, notice that C2 has 2 possibilities, C5 has 2 possibilities, and so therefore there are 4 possibilities that those 2 things could begin. It could be 0, 0, 0, 1, 1, 0, and 1, 1. Those are the 4 different ways we can test these 2 components. If one of them, let's say C3, had 3 different things, then we would have 6, 3 times 2. But in this case, it is 2 times 2. What we need to verify is that in these 2 columns, there is a 0, 0 somewhere, which is clearly right here. We need to verify that there's a 0 in the second column and 1 in the 5th one. So it's not here, and it's right here. So there's a 0, 1 right here. We need to verify that there's a 1, 0 somewhere. So it's not here, not here, not here, not here, not here. And finally, in the very last test, there's a 1, 0 here. And then we need to verify there's also a 1, 1 somewhere. So there's a 1, 1 right here. And so therefore these columns, these pair of columns are what are called covered. Because no matter how we test these pair of columns, some test will contain that pair for these 2 different components. And what we guarantee, and you can check this for yourself, is that no matter which pair of components you pick, and no matter which combination you pick, it will appear in at least one test somewhere. And that's what's called a covering array. So the notion that we use for this is CA, standing for covering array, of course. Then the number of rows goes here, and that's going to be denoted by n. Then a semicolon, followed by what is called the strength. So the strength is how many columns you pick at each point. So here we have a choice of 2, and I said no matter which pair of components you pick, you'll find every single pair of values appearing at least once. So that's what we call T, and in this case it's going to be 2 because that's the number of components that we picked. Then the third thing is going to be the number of columns in the thing. So in this case there are 5 different components, and so the K value, which is the number of components, is going to be 5, and then the number of values is going to be the very last thing, which is how many things appear in each of the components, columns, and so that's going to be called the V parameter. What I claim that this matrix looking thing here, that's going to be a covering array with 6 rows, because that's pretty clear to see here. The strength is 2, because I claim that you can pick any pair of columns here and get that coverage property. The number of columns is 5, and the number of values is 2. And so what I claim is that I can make a covering array with 6 rows, strength 2, 5 columns, and 2 different what are called symbols. And what we want to do is we want to make testing as efficient as possible based on the motivation we discussed earlier. So what I want to figure out is, given the last 3 parameters, so t, k, and v, what is the minimum n such that a covering array with that many tests actually exists? And that's a very wide open question. There are a lot of different parameters that the answer is actually known and is proven to be optimal, but we don't know the answer in general. So what we usually do when we have a very hard question like this, which is purely mathematical, what we want to do is we want to find bounds on how big the arrays can get. That's what I'm going to do here with something called the probabilistic method. Okay, I just restated the question that we were trying to answer right here. We're given the strength, the number of columns, and the number of symbols, and we want to figure out what is the minimum number of rows, mainly the number of tests, such that this covering array actually exists. Let's try to visualize what this thing looks like. So let's say that this thing actually is a covering array NTKV. So let's assume that this thing we claim to be a covering array and someone asks us, prove it to me that it actually is a covering array. Well, what they can do to disprove us is to find some set of columns, some set of t columns, because that's the strength here. So some set of t columns, let's say it's 4 just as an example. And some valuation, so it's going to pick some value v1 here, v2 here, v3 here, and v4 here, such that the quadruple in this case, v1, 2, 3, and 4, doesn't appear in those columns in this array anywhere. And what we want to do is we want to assure them that it actually does appear there. So how would we actually show this? Well, what we can do is we can use something called a non-constructive proof. I can guarantee there exists an array that does the thing, that has these properties, but we can't necessarily generate it through this method. It's a very nice way of using mathematics to predict that there actually exists an array without having to make one ourselves. Let's think about how we would actually generate this. Well, if you don't know what to do to solve a particular really hard problem, one really nice method that you can do is just make something completely at random. Just see what happens. What is the general behavior if we just try to make this thing completely randomly? What happens? So let's say that the way that we're going to make this is I'm going to have an array of this size. So an array of size n times k. So this is the number of rows. And obviously I don't know what n is because we're trying to solve for n, but let's just assume that we know what n is and then solve for it later so that the equation that we're going to make holds. So let's just say that n is some number that we will eventually come up with. And k is given to us, so that's the number of columns. And what we're going to do is we're going to generate this completely randomly. So a random array in this sense means each of these entries right here is going to be uniformly at random. So uniform just means I'm not going to have any bias as to what value actually appears there. Just pick one uniformly at random. And each of the entries are going to be independently picked. So each of these entries is not going to depend on any other entry in the array. So everything is its own random variable, so to speak. And so that's how we're going to make this random array. So just knowing a little bit about the problem can actually make this part that we're going to do right here much easier. So in this array, we're going to be calculating some kind of expectation thing. So some kind of average over a bunch of different variables. So we create a bunch of variables and we're going to calculate some kind of expectation. Well, one thing that we can do is, let's say that we wanted to calculate the expectation of the number of missing interactions. So the proof, so to speak, that this thing is not a covering array is that there's a missing what is called an interaction. Interaction here just means a selection of columns with a selection of values, and they don't appear anywhere, which is what it means to be missing. So the number of missing interactions is going to be some kind of distribution because we're going to be selecting things uniformly at random, mainly at random, but it's going to be some kind of random variable right here. And so therefore it has an expectation. Well, if the expectation is strictly, importantly that it's strictly less than 1, so the expected number of missing things is strictly less than 1, then that means if we visualize the number line right here, well, the number of missing things can't be less than 0. You can't have like a negative number of things missing. So it's going to be at least 0. And let's say here's 1. And it clearly can be more than 1s. But let's say the expectation is right there. It's a little less than 1. Then that means that there must be something that is to the left of this, because the expectation is the average. And so there must be something to the left of it. So if there's something to the left of this, it must be 0. Why? Because the number of missing interactions must always be an integer. And so if it's to the left of something that is strictly less than 1, then it must be at 0, because 1, there's nothing to the left of 0, and namely that there's only 0 right here. And so if this is the case, so if the expectation is less than 1, strictly less, then there exists a covering array. So this is a really nice tool to know that you're calculating something that you know is an integer, but the expectation could be anything. It doesn't have to be an integer. But if you force the expectation to be less than an integer, then there must be a covering array that exists that lands at 0, which is exactly what we want. So what we need to figure out is, what is the expectation, set it less than 1, and then solve for the number of rows. If we make the number of rows longer and longer and longer, then clearly this expectation is going to go down, 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 and eventually it's going to go less than 1, which is what we want. Let's calculate this expectation. So what is the expected number of missing interactions? Well, the expected number of missing things is really easy to calculate. It's simply the number of interactions that exist at all times the probability that they're missing. Because the array is completely uniform, each of the entries is uniformly chosen at random, completely independently, so we can treat each one of them completely separately. Well, if you stare at the problem long enough, the number of interactions is going to be k choose t times v to the t. So the k choose t is the number of column choices, and the v to the t thing is the number of values for those t columns. Why is there a choice here and v to the power t here? Mainly because we can't pick a column twice, whereas we can pick values twice. So what's the probability that something is missing? Well, it's exactly the same probability that it is missing in one row times the probability it's missing in the next row times the probability it's missing in the next row, and we just multiply all those together. So if you stare at it long enough, it's going to be this probability. So this is the probability that you actually don't get the specific choices of values in a particular row to the power n, because that's the number of rows that we have. So the 1 minus v to the t, that's the probability that it's missing, some interaction is missing in one row. And the n power, because every row is chosen exactly the same over the same distribution, we can just take it to the power n and then we're done. And then we just solve for when this is less than 1. All you have to do is now just solve for this n thing upstairs. So if you solve for n, what you get is that n is less than or equal to v to the t times log k plus some other stuff. And this isn't actually the exact constant that you get, but it's close enough. Whereas the old way of doing things, which is to do a complete exhaustive enumeration, is that n is going to be equal to v to the power k. So notice that if t is a very small number, then v to the t compared to the v to the k is way smaller. And even if k is huge, like 1 billion or something, you're only multiplying by the logarithm of this. Therefore, this is going to be a lot smaller than this in general, which is really nice. So this first thing is going to be smaller than the second thing every single time. And you may think, well, if this is the upper bound, what is the lower bound? It turns out that you can get a lower bound, which is approximately log k on the lower end too. So some constant times log k. So the optimal size of these arrays is going to be some constant times log k, at least asymptotically, which is really, really cool. Hopefully you learned something about the probabilistic method for covering arrays, or at least the probabilistic method in general. It's a really nice mathematical technique to assert the existence and give some additional motivation for why we care about these things. These objects are much smaller than just try every combination, which is really important in a practical testing scenario, as you might imagine. So hopefully that was interesting. Leave thoughts about this research into the comments down below. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.